SwayamPrabha. Digital India. Educated India.
In this lecture, let us discuss about high-speed intakes, a little bit about scramjet engines, and then we move on to other applications of shock waves, which cover domains like medical, atmospheric like volcanic, and detonation waves which can occur under different situation circumstances like explosions and so on. To begin with, we look at intakes. This is a very interesting area and is an extremely important issue related to all kinds of air breathing engines. We see a graph here where the x axis indicates design Mach number of a particular intake and the total pressure recovery. The maximum possible is unity, of course. And then you see different kinds of intake configurations which have been sketched here, which work in different design Mach number ranges. So, this configuration refers to this band, the second one to this band, the third one to this band, and so on. And this particular plot has been taken from this reference. Supersonic inlets involve shocks to decelerate the flow to subsonic engine phase Mach numbers. So, if you are talking about an engine which operates at subsonic Mach numbers, but the vehicle is traveling at supersonic velocities, then you ought to decelerate it to a subsonic Mach number range before you feed it to the engine. For engines which operate on subsonic through flow like turbofan, turbojet engine, the deceleration to subsonic Mach number implies placement of a normal shock somewhere in the inlet stream. So, that is one possible way of slowing down the flow. This happens to be an effective solution for low supersonic Mach numbers, typically in a range like this 1.5 to 2.2 or so on, which this band essentially indicates. And you can see that as the Mach number increases, there is quite a dramatic fall in total pressure recovery. That means the total pressure losses are increasing quite dramatically with the increase in Mach number. Beyond this Mach number range, the normal shock deceleration becomes inefficient, which is evident from this plot, as it creates excessive total pressure loss. To extend the operational Mach numbers to around 2.5 or slightly more, a better way of slowing down the flow, that means by creating less amount of total pressure loss, is to decelerate the flow through external compression ramps like the way it has been shown over here, or cones, which is the case of a three-dimensional ramp, prior to the appearance of the normal shock near the cowl lip. So, the normal shock forms somewhere here. This type of inlet is called as an external compression inlet. So, external compression inlets are shown in this figure. The cowl wave drag is the limiting performance parameter for the external compression inlet, and when the normal shock is pushed out into the ramp, which is called as the subcritical mode, the shock induced flow separation causes a shock or shock flow oscillation, which is called as a bus instability. So, in case that kind of a situation arises where it is pushed out into the ramp, there is a possibility of buzz instability. There could also be intake unstart. To operate without buzz or simply to widen the stability margin of external compression inlets require the boundary layer removal from the compression ramps and incorporating a throat slot for bleed purposes. To reduce the cowl wave drag at higher supersonic Mach numbers beyond 2.5 leads to internal shock reflections, and an internal throat has to be used. So, that is typically talking about a configuration like this, where the throat essentially goes further inside. Such inlets are called mixed compression inlets, which produced highest overall performance in the free stream Mach numbers of about 2.5 to 5. So, you are able to push the maximum Mach number range to almost 5 here. Of course, by then the total pressure recovery also has dropped quite a bit, but you can imagine that if you were using the other two options in this Mach number range, there would have been further dramatic reduction in the performance. So, that way the mixed compression intake does pretty well in this comparatively higher Mach number range. The internal throat creates another form of instability, namely the starting and unstarting instability of the inlet. Variable geometry throat offers a practical starting approach to mixed compression inlets. So, variable geometry throat would undo such kind of disadvantages like unstart. To avoid intake unstart, inlet back pressure needs to be controlled through a shock trap with a fast acting bleed valve and a bypass secondary flow control valve integrated in the subsonic diffuser. So, there are different ways of handling that problem, and then finally, you are able to achieve reasonably good performance at slightly higher supersonic Mach number ranges. The thrust penalty for the boundary layer bleed is the price to be paid for deploying a mixed compression inlet. For hypersonic Mach numbers, when we are pushing to higher Mach numbers, internal compression inlets offer the lowest engine installation wave drag. That means that is definitely the choice. You are going to have this kind of a choice. In addition, flow deceleration through multiple shocks and their reflections inside a duct is preferred over fewer shock decelerations. That means you are talking about the flow getting slowed down with multiple reflections of the shock wave further inside the engine. However, the normal shock can be eliminated if the engine design allows for a supersonic through flow. Now, if the engine is going to work at subsonic Mach numbers, you do not have a choice but to create a normal shock, which obviously will lead to a significant P naught loss. Only thing is that if you can create that normal shock at a reasonably low free stream Mach number by gradually slowing down the flow through oblique shocks before you create the final normal shock, then the P naught loss will be minimized. However, if the engine is operating in such a manner that it can handle supersonic through flow, then you do not really need to create such kind of a situation. A supersonic through flow and a supersonic combustion ramjet, which means scramjet, are examples of this kind of modern thinking in hypersonic propulsion. So, these are concepts which would really work as the Mach number goes higher and higher in terms of more advanced applications. A very important performance metric is the specific impulse for all kinds of propulsion devices, including rocket engines. The specific impulse achieved by a chemical rocket is independent of vehicle speed. So, you have the specific impulse in terms of seconds on the y axis and the flight Mach number along the x axis. This is the reference from which the figure has been taken, the book of Farokhi, and there you find that a few abbreviations have been used, where TJ, RJ, CRJ respectively mean turbojet, ramjet, scramjet, and then at the bottom you have rocket, and then you note that for hydrocarbon fuels you have a certain set of plots, and for hydrogen those plots get pushed up in terms of specific impulse. Keep in mind that hydrogen is a very low molecular weight fuel, but with a lot of calorific value. So, keep that consideration in mind when you think about the specific impulse consideration. Now, as is evident from the plot, chemical rockets have specific impulse which is independent of vehicle speed. This is because it does not suffer from any ram drag penalty as the Mach number increases. Also, the fuel combustion within the rocket engine is not affected by stagnation temperature rise in the engine intake. due to increase in free stream speed as the vehicle accelerates through the atmosphere. So, this happens to be a major limitation for the air breathing engines, but it does not act as an impediment for rockets. The specific impulse for chemical rockets typically vary in this range, which is rather low compared to many of the air breathing engines. The specific impulse for air breathing engines is shifted upward when hydrogen is used in place of hydrocarbon, which we already mentioned. Gas turbine engine achieves takeoff thrust and best load speed performance as depicted by specific impulse range of about 4000 to 8000 seconds for turbojet, slightly better for turbofan. Specific impulse of a gas turbine engine drops with flight Mach number. The rapid fall of a gas turbine engine performance with forward speed is averted if one switched to the ramjet family of air breathing engines. That means, as the turbojet engine's performance droops down, you need to switch to a ramjet configuration to recover the performance at still higher Mach numbers. From around Mach 3, a conventional ramjet starts to outperform a turbojet. Also, the ramjet becomes self-starting because automatically the air gets compressed at the intake before it is combusted, and therefore, you do not really need a conventional compressor to compress the air. Rather, the conventional compressor becomes redundant, kind of non-functional at Mach 3 onwards. Again, the rapid flow of a conventional ramjet engine performance with flight Mach number is halted if we switch to the rapid fall of a conventional ramjet engine performance with flight Mach number is halted if we switch to the supersonic combustion ramjet, which is called as the scramjet, at a flight Mach number of around 6 onwards. At around Mach 6, a scramjet outperforms other air breathing engines, and then at those Mach numbers you do not have any other possibility from the air breathing family. Of course, the rocket engines still remain, but as far as air breathing engines are concerned, that is the only possibility that you have. The deterioration of scramjet performance with forward speed is inevitable as the flight stagnation temperature increases and the components losses become larger and larger as the Mach number goes up further. The upper operational Mach number of scramjets is unknown at this point because it is basically being researched. It is suspected that once it reaches about 10 to 15 Mach number, the performance will fall below that of chemical rockets. So, there is a possibility or a suspect is there that that SCRJ will follow the trend and go below that of the rocket, and therefore, at still higher Mach numbers the rocket becomes the only viable engine. So, typically this is the entire range that we are talking about, and then if we want to elaborate a little further on the scramjet engine, this is a very good reference which you can read, and this is typically a sketch taken from that reference with the different station numbers marked with the schematic following standard nomenclature for cycle analysis of air breathing engines. The scramjet engine belongs to the family of Brayton cycles. So, if you have learned the thermodynamic cycles, then you must be familiar with this already, which consists of two adiabatic and two constant pressure processes. A simplified schematic diagram of a typical scramjet equipped vehicle is shown above. So, basically the engine part lies somewhere here. The vehicle in general has a larger body. We have looked at this aspect even in some earlier lecture when we were talking about trajectories. It is inevitably a lifting body from the kind of shape that we are talking about. It is not a kind of body which will have a ballistic kind of a journey. The vehicle's forebody performs a large part of the inlet compression. When the free stream reaches the body, there is essentially a compression wave, an oblique shock reaching all the way up to the engine cowl. This we have discussed in the context of shock-shock interactions too. The vehicle's forebody performs a large part of the compression through this process. The afterbody constitutes part of the nozzle. So, we are talking about this part of the vehicle. and the engine therefore occupies the entire lower surface of the vehicle, which we have already encircled. The station 0 represents free stream, station 1 represents the beginning of compression. Hypersonic shock wave angles are going to be small, as we remember that typically right from the week 1 discussions, we said that the hypersonic shocks stay very close to the body. This results in long compression ramps or spikes if an axisymmetric configuration is used, and the compression begins at the vehicle's leading edge. Additional compression takes place inside the inlet duct. So, further inside also there is compression which is possible. And then if you look at station 2.1, then that represents the entrance into the isolator section. The role of the isolator is to separate the inlet from the adverse effects of a pressure rise that is due to the combustion in the combustion chamber. So, insulating from the pressure rise is what the isolator does. That means isolating. The presence of a shock train in the isolator further compresses the air before arriving at the combustion chamber. So, the inlet is isolated that way through that device. Though thermodynamically it is not a desirable component, because it will lead to further pressure losses and increase the engine's cooling loads. It also adds to the engine weight and reduces its reliability. However, operationally it is needed to include a shock train that adjusts such that it fulfills the role which we described just above. Station 3 is the combustion chamber. Entrance in, unlike the turbojet engine cycle in which air compression ratio is controlled by the compressor settings, where we talk about pressure ratios, in a fixed geometry scramjet, the pressure at the combustion chamber entrance varies over a large range. Station 4 is the combustion chamber exit and the beginning of the expansion. Station 10 is the exit from the nozzle. Because of the large expansion ratios, the entire aft part of the vehicle may be part of the engine nozzle. So, these are the primary stations and the different processes which go through the scramjet engine. A little bit more on the flow and combustion processes, typical time scales. So, this is a typical figure taken from Warnot's book, related to the chemical time scales on one hand and the physical time scales, and then you see that on the upper end in the chemical time scales you see the slow time scales, frozen chemistry, and the fast time scales, equilibrium chemistry, and then the time scales of flow, turbulence, transport phenomena on one hand, and equilibrium or partial equilibrium assumed in the other. So, that way we are able to see the typical magnitudes, ranges of magnitudes where the different time scales operate. There are large differences between the time scales of the physical and chemical processes typically encountered in a supersonic combustion ramjet. Assuming a vehicle flying at the low end of the hypersonic regime, that means typically Mach 6 to 8, the combustor entrance Mach number is expected to be in this range as you slow down the flow, but still the flow remains supersonic when you make it enter the combustor. As we mentioned earlier, that we do not need a normal shock to terminate it into a subsonic flow, because there will be enormous stagnation pressure losses. Thus, in a reasonably long engine of no longer than several meters, the fluid residence time is of the order of few milliseconds. Now, this is the time available for aerothermal processes to be completed efficiently, so that heat can be extracted from the fuel and thrust can be produced in the engine's nozzle. Gaseous fuels must penetrate into the airstream following injection and mix to a molecular level, so that the molecular collisions can result in chemical reactions and heat release. Additional processes exist in which condensed phase fuels are used, including jet breakup and droplet vaporization. Of course, these are more involved topics which we are not really getting into. So, this reference is important for looking at the time scales. Depending on the temperature, pressure, composition, concentration, Chemical reactions in general can span over a vast range of time scales, typically in this huge band. Molecular transport, on the other hand, can occur within this band. The fast chemical processes would create equilibrium conditions, and long chemical processes will create frozen conditions. In these cases, chemical processes can be uncoupled from the flow field analysis. However, that kind of situation is generally not encountered in scramjet engines. From a chemical kinetics point of view, the time required to complete the exothermic reactions results from the addition of the ignition delay time and the burning time. So, that is the time during which the heat release from the combustion process will actually take place. So, time scales are extremely important, and here we are trying to see some possible configurations which may be used to effectively inject fuel into a supersonic stream, stabilize, establish a flame front, and then stabilize it, keep it stabilized. So, that is a huge challenge in scramjet engines. So, this is one possible configuration, while this is another schematically represented, of course. So, in the left hand configuration, you see that there is some kind of a step like structure over here. So, this is the base region of that step, and you have a supersonic free stream approaching from left towards the right. So, there is a 2D recirculation region which is formed, which is shown over here. The boundary layer formed upstream of the step is pushed by the expansion. So, this is the expansion wave which is formed at the lip. The other day when we were discussing about shock diffraction, you have seen a bit of that. A shear layer formed between the boundary layer and the recirculation region brings fresh air in the region. The fuel is injected into the recirculation region, and a barrel shock forms at each injection orifice with shear layers in which the flame is initiated following mixing and heat exchange between the hot gases in the region. So, this is where you would expect that a flame would be established and stabilized. So, this is one possible configuration where you can actually have a stabilized flame established in a supersonic flow, cross flow, while this is another where you have a supersonic cross flow approaching and orifice which is wall mounted, from which you have a transverse under expanded jet being injected into the supersonic airstream. The injected plume forms a barrel shock. So, this is the structure of the flow field where the barrel shock would be formed, generating a bow shock that leads to separation and formation of a recirculation region in front of the jet. Vortices would spill around the barrel shock, and they would bend and turn downstream. An additional recirculation region would form at the jet downstream stagnation point. So, this may be another way of fuel injection and flame stabilization. Of course, we saw them in a schematic manner, not going deep into the actual configurations which do operate in such supersonic combustors, but that gives you some idea. Again, from the same reference, we have taken these two figures along with the reference at the bottom of McClinton, where we see the combustion chamber design includes a constant area for rapid heat release, followed by the portion of the expanding area where additional heat can be released in ramjet operation, and subsequent expansion can take place in the internal nozzle. So, you have two possible configurations operating in two different Mach number ranges. The comparatively lower one is the dual mode scramjet. You can see the isolator over here, and then you have the combustor, the fuel injection happening further downstream. You see the shock train over here. You see the inlet further upstream, and then in the other configuration which operates at still higher Mach numbers of about 7 to 15 plus, you see the injection happening further upstream, and then you have a train of shocks here. So, the configurations differ between the two Mach number ranges, and thereby you have the ramjet isolator in the lower Mach number range and the scramjet isolator, the configuration for scramjet on the right hand side figure. So, with that we looked at intakes and some amount of flow processes and combustion as they occur in scramjets. We move on to the next topic here, where we look at some other applications of shock waves. What we mean by this word other is not the ones which have been discussed widely in the last several weeks of the course, where we mainly looked at aerospace applications of shocks, but that is not their only applications, and their applications are widening with time. One of them being medical applications, that is the first one we will take up, followed by detonation waves, which may be occurring in situations where fuel burns, very rapidly forming shock ahead of the front. It may also happen in the case of explosives. Then shocks which may form in volcanic eruptions, and finally shocks which might occur in astrophysical flows. Beginning with medical applications, this is the reference from which we have taken this figure: extracorporeal shock wave lithotripsy in clinical practice by Schmutz et al., published in 2019. And then what you see in this diagram is a urological multifunctional table with shockwave lithotripsy generator. So, you have an operating unit here, the X-ray unit at 2, the examination table where the patient would be located, and the shockwave generator which is beneath. So, these are the primary components of the device. And then if we are going a little deeper into what the process is all about, we have made use of this small diagram which has been taken from Johns Hopkins website, where you can see that shock waves are being focused at some portion of the kidney, affected kidney, where kidney stones have formed, and the basic idea is to fragment them and then release them through urine through the ureter. We begin by trying to address the question that what is lithotripsy. It is a non-invasive or non-intrusive procedure used to treat kidney stones that are too large to pass through the urinary tract. So, until unless you fragment them here in this region, they would never pass through the tract. And what we mean by non-invasive is that such a procedure would not happen by piercing the patient's skin. Lithotripsy treats kidney stones by sending focused ultrasonic energy or shock waves directly to the stone, first located with fluoroscopy, a type of X-ray movie which identifies the stones, or through ultrasound, which is high frequency sound waves, which identifies the presence of stones. The shock waves break a large stone into smaller stones that will pass through the urinary system. So, this is basically a process of fragmentation which is achieved by use of shock waves. Lithotripsy allows the removal of stones in the urinary system to avoid an invasive surgery procedure for stone removal, which we already mentioned earlier in the above point. And then we move on to the next slide, where we say lithotripsy involves the administration of a series of shock waves to the targeted stone or stones. The shock waves, which are generated by a machine called a lithotripter, are focused by X-ray onto the kidney stone. The shock waves travel into the body through skin and tissue, reaching the stone, where they break it into small fragments. There may be some damage to surrounding tissues as the shock waves propagate through the body, through the skin, through the tissues, but by appropriate focusing of shock waves, that kind of a damage could be minimized. With more advanced treatments coming up these days, that should be achievable, that the damage to surrounding tissue should be minimized. And how you can achieve that is through appropriate focusing of the shock waves. For several weeks following the treatment, those small fragments are passed out of the body in the urine. So, this is broadly the procedure. We move on to the next application, detonation waves. The detonation wave is an explosive gas mixture, or rather in a explosive gas mixture is a shock wave produced by the rapid combustion of the mixture, sufficiently intense to cause almost instantaneous ignition of the gas through which it passes, and continuously maintained by the combustion thereby started. We again try to stress the point by saying the heat released from the reactions that follow the shock wave drives the shock wave. So, this is broadly the idea. You have a explosive gas mixture and a shock is produced by the rapid combustion of that explosive gas mixture, and then as the explosive gas mixture front propagates, it keeps driving the shock wave which is in front of it. So, that is basically the detonation wave phenomena, and you could see a very interesting YouTube video posted here, detonation initiation and exhaust of a pulse detonation combustor, which will be really very illustrative. You could also look at other references where works on detonation waves have been reported, which are rather recent communications. So, this is one, the other is one which is below. So, a little bit about detonation waves, we are not elaborating too much beyond this, and then we look at a little bit about how shock waves may happen in the case of volcanic eruption. So, this is typically a figure from the paper The Fluid Mechanics Inside a Volcano, authored by Konnerman and Manga in Annual Review of Fluid Mechanics 2007, where we find that different locations of volcanic crater are illustrated over here. We will go over to the bullet points to have a better understanding. So, the figure shows a schematic illustration of a volcano. Magma, which is colored in red, that flows out of the crater contains dissolved volatiles, predominantly it is water, carbon dioxide, sulfur dioxide and so on. Upon ascent driven decompression, so as it ascends it decompresses, as it moves up through the crater it decompresses, that means the pressure reduces. So, volatile solubility decreases and magma becomes supersaturated in volatiles, which basically means that gas bubbles nucleate at the solution surface, and they are actually indicated through these white bubble like structures here. Volatiles continue to exsolve and bubbles grow during magma ascent above the solution surface, and gas may be lost from the magma by permeable gas flow through porous and or fractured magma. Gas may also expand radially into conduit walls or vertically through the magma column to the atmosphere. Therefore, there is a lot of gas evolution because the bubbles are growing due to this decompression. During explosive eruptions, bubble walls rupture catastrophically at the fragmentation surface. The released gas expands rapidly and magma ascent changes from a viscous melt with suspended bubbles to a gas flow with suspended magma fragments, and these are usually released at extremely high velocities in the form of very energetic volcanic plumes. They could be so fast that this basically may propagate through the crater in the form of a shock front, moving up and releasing into the atmosphere several kilometers or tens of kilometers at times up into the atmosphere. So, this is a typical view of Sakurajima vent before eruption, indicating the area of interest used to extract the wave structures. This happened sometime on 30th January 2011, and essentially the bottom pictures are a sequence of images which have been obtained by looking at how the magma moves out through the crater vent, and you can see the time scales from 0 to 0.2 seconds. There is a shock like front which is moving up and trying to go out and release into the atmosphere. In the series of pictures showing the shock wave displacement, the shock front is highlighted by red line as a function of time. So, if you are interested, you can go through this reference and you can clearly make out from these pictures that it is a very interesting phenomena where we can actually try to look at it from the point of view of a moving shock front, like the way we saw in the shock tube problem. In fact, in this paper they have tried to model it by using such an analogy. And this is another very interesting phenomena, that is this is basically the eruption of the Honga Tonga volcano sometime in 2022 January 15th, and it has been captured through images, video images in fact, from the GOES 17 satellite of NASA. It is available, the details are available in this website, and you can actually see the video image or the kind of image sequence, and from the movie these different instantaneous images have been extracted. You can definitely go through this site and see it once more. We can see the images of the umbrella cloud that is generated by the underwater eruption of the volcano, and crescent shaped bow shock waves, numerous lightning strikes. They are also visible with close scrutiny if you go through the video's image sequence. One thing that you can make out is from the early times of initiation to a slightly later time and further, you can clearly see fronts developing within the emerging magma, which are essentially the bow kind of shocks which are coming out of the crater. So, with that we conclude by saying that in this lecture we discussed about high speed intakes for air breathing engines. We then discussed flow and combustion issues in scramjet engines, very preliminary exposure of that. Finally, we discussed about some other applications of shock waves, including medical applications, detonation waves and volcanic eruption. Thank you.